Chapter 21 will cover the reactions of carboxylic acid derivatives, specifically a reaction called nucleophilic acyl substitution reactions. Before we begin covering acyl substitutions, let's review some of the functional groups we're going to encounter in this chapter. All of these functional groups are related in that they're all acid or carboxylic acid derivatives. Acid chlorides are compounds that contain a chlorine attached to a carbon with a carbonyl. Simple example is acetyl chloride, which is shown here on the right. Acid bromides contain a bromine that is attached to a carbon with a carbonyl or is part of a carbonyl. An example is benzoyl bromide. Acid anhydrides, or simply anhydrides, are compounds that contain an oxygen in between two carbonyls. A simple example is acetic anhydride. Esters contain an alkoxy group attached to a carbon of a carbonyl. A simple example is ethyl acetate. And amides contain an amino group attached to a carbon that is part of a carbonyl. A simple example is acetamide. Amides can be further subdivided into primary amides, secondary amides, and tertiary amides. Primary amides contain no alkyl groups, and therefore the nitrogen of the amide has two hydrogens. Secondary amides contain one alkyl group, and they have, as a result, a hydrogen on the nitrogen. And a tertiary amide contains two alkyl groups on the nitrogen, and therefore no hydrogens on the nitrogen. Esters are well known for, at least simple esters, are well known for the smells, the pleasant smells that they contain. For example, isopentyl acetate is responsible for the smell that we normally associate with bananas, and methylbutanoate gives apples their typical aroma. There are two additional acid derivatives that you should be familiar with. Although they're often not used in organic synthesis in a typical organic lab, they are important acid derivatives when it comes to biological systems. So those two acid derivative functional groups are thioesters, which contain a sulfur attached to a carbonyl, and acylphosphates, which contain a phosphate group attached to a carbonyl. These functional groups we're going to cover, or we're going to see a few examples as we go through this chapter, but in general, they're not really used in organic synthesis. Here's an example of a molecule that contains a thioester. You can see that here on the right side, there's a carbonyl with a sulfur. This is acetyl coenzyme, which is a thioester. We're going to look at the importance of this thioester later on this chapter. With the exception of carboxylic acids and primary and secondary amides, most acid derivatives will interact with each other through dipole-dipole interactions as well as London interactions. As an example, here is an ester. It has a boiling point of 32 degrees Celsius. An acid chloride has a boiling point of 51 degrees Celsius. Compare that to a carboxylic acid, which has a much higher boiling point. We could explain this by the fact that carboxylic acids interact with each other through hydrogen bonding, while an ester and an acid chloride would interact with each other mostly through dipole-dipole interactions as well as London forces. A primary amide, such as acetamide, has a very high boiling point of 221 degrees Celsius. This is because it's able to hydrogen bond. In the case of a primary amide, it can actually form more hydrogen bonds compared to a carboxylic acid. So that sort of explains why a primary amide would have generally a higher boiling point than a carboxylic acid and even an alcohol. In this example, you might notice that the acid chloride has a slightly higher boiling point than the ester shown, even though they're similar molecular weights. The chlorine is a heavier atom than oxygen and carbon and hydrogen, which are found in this ester. And so for that reason, it leads to a slightly higher boiling point for the acid chloride.